Okay, this is the lesson on the last lesson of this unit, which is on spheres. Okay, so put your heading, put down the title of the unit: prisms, pyramids, cylinders, cones, and spheres. And then this is number 5, spheres. All right, we have a critical concept for spheres. We want to apply the properties of a sphere, including the intersection of a plane and a sphere is a circle, and we'll see that. A great circle is the largest circle that can be drawn on a sphere. Okay, and two planes equidistant from the center of the sphere and intersecting the sphere do so in congruent circles. And the surface area is 4 pi r squared, and the volume is 4/3 pi r cubed. So there are a lot of critical concepts when it comes to spheres, and we're going to cover each one of those. All right, just hang on one second. Okay, I just had to get my makeshift spheres. All right, now let's see. Spheres are three-dimensional closed surfaces. A sphere is a set of points in three-dimensional space equidistant from a point called the center. The radius of the sphere is the distance from the center to the points on the sphere. Of all shapes, a sphere has the smallest surface area for its volume. A cone is similar to... let's forget that. That was in the last lesson, and I forgot to delete it. Okay, there we go. Let's draw a sphere. All right. This is typically the way that spheres are drawn. Okay, you start off with a circle. Okay, like that. And then this looks like just a circle. So to make it look like a sphere, what usually we do is we make a curved part like that going across the middle, and then like a dashed line as if this part was in the back. That's typically how we draw a very simplified sphere. Okay, that kind of shows you that this is in 3 dimensions. So this is the top radius. All right, so if we're looking at this apple and this is a sphere, the first circle is this top circumference, and then this other circle in the middle is supposed to be like the equator of the apple. Okay, so let's just label the one thing that we have when we talk about spheres, and that's the radius, the distance from the center to the edge. R is the radius. That's the one nice thing about spheres, is that all you have is a radius, and all the formulas just use the radius. So let's turn this over. So the volume of a sphere can be calculated using the following formula. Volume equals 4/3 pi r cubed, where V is the volume and R is the radius. Let's draw another sphere just for practice in this space provided here. Okay. Okay, and we'll draw a radius this time going up this way. Doesn't matter. Alright, that's good enough. Let's go to the surface area part. The surface area of a sphere can be calculated using the following formula. Alright, now let me just check something. So the volume is 4/3 pi r cubed. You see, the only thing we care about is the r in this problem, and it's cubed. In this problem, again, all we care about is the r, and this time it's squared. And instead of 4/3, it's just 4. Or if you're given the diameter, you can also use pi d squared, but let's not even use that one because we could always just turn the diameter into a radius. So why remember two formulas when you can just remember one? Okay? Again, let's draw another sphere for practice in this space. Okay? And the surface area is essentially the skin of this apple, right? It's all of the area around the outside of my sphere. Okay? And the volume is everything inside the apple. All the meat in this apple is the volume. So, next page. Okay. This is where we're going to need to draw something. A cross-section of a geometric solid is the intersection of a plane and the solid. Okay? So, for example, if I had a cube, right? A rectangular prism, let's say. Right? Let's say I have this rectangular prism. I can slice that with a plane. So let's imagine a plane coming down and slicing this thing. In half. Okay? Right? So this plane sliced this thing in half, and we opened it up, right? So what you would have when you opened it is essentially one side would be a square and the other side would be a square or a rectangle. They would be like that. Okay? Now let's think of what else. Say we had a cylinder. I'm trying to draw this as best I can. It's not easy to draw these things. And let's say I sliced a cylinder with a plane. Right? So, and then let's say we opened up that cylinder. Okay? What you would have is two circles. So imagine that I took this and I sliced it right down the middle and then I opened it up. Okay? What you would have is two circles. Now, so let's think about a sphere. I wish they gave me a good picture of what it looks like to slice a sphere with a plane. But let's say we had a sphere. Right? And we sliced the sphere with the plane. Right down the middle of the sphere. Okay? Let's see. How could I draw that better? this. Maybe this part shouldn't be colored in. I don't know if that would look any better though. So let's say I slice this sphere with the plane. So here's what's happening. This is why I got my apples out. I have a sphere, right? And I'm slicing it with the plane. So you can imagine I'm taking a plane and slicing. This is what I'm trying to draw. Right? I'm slicing the sphere with a plane. You see that? That's what we're trying to imagine. Now, what was this going to look like when I pull it apart? That's the question, right? What is this sphere going to look like when I pull it apart? And you'll see what it looks like. Two circles. Okay? So when you slice a sphere with a plane, when you slice a sphere with a plane and you open it up, the cross section is two circles. Okay? Can't get a better demonstration than that. So it's similar to a cylinder, but we could slice a cylinder in a different way also. Right? So anyway, maybe this goes like that? I don't know. I don't know. It's tough to draw that, and I'm not that great of an artist. So, a great circle is the largest circle that can be drawn on a sphere. Such a circle will be found when the cross-sectional plane passes through the center of the sphere. Okay? So, notice when I drew this, my plane did not go through the center of my apple, right? It didn't go through the center of my apple. So I got two circles that are the same size, but they're not the biggest circles that I could have gotten. I could have gotten what's called a great circle. And in order to get a great circle, you have to cut the sphere in half, directly through the center of the sphere. So what I would have to do is use my cutting plane and go right through the center of the sphere. Now those, pretend they're circles, right? They're close enough. Those are the biggest circles that I can get because I cut through the center. See, look at the difference in the size. Okay, this one is bigger than this one. Okay? And the farther away from the center that I cut this thing, the smaller the circles get, right? So I have that one, and if I get a little closer to the center, I have that one. And then if I get right in the center, I have the biggest one. And doesn't get any bigger than the one that goes through the center. Okay? Now, that line that goes around the center, all right, the biggest line, I don't think I can draw on this that well, but this line, okay, this line that created the biggest circle, that's called a great circle, okay? The equator is an example of a great circle, right? If you took a globe and you cut it around at its biggest width, right, like if this was the Earth and we cut it right along the equator is the great circle. It's the biggest circle that you can get. And that happens when your slice goes through the center of the sphere. Okay? The equator is an example of a great circle. Meridians passing through the north and south poles are also great circles. So, let's try to draw a sphere. Let's draw a sphere again. Maybe we can draw a picture of this. Maybe not. Circle. Now, essentially this line that goes around the middle, and let's say it cuts right through the center, this would be a great circle. Okay? This line on the outside, well, let's just say it's that one. Okay? Now remember, there are an infinite number of great circles in a sphere, right? Because I can go right through the middle of my sphere like that, right? That line is like the equator. That line's a great circle, all right? But I could also just move my rubber band a little bit this way and a little bit this way, and I have another great circle, right? Or I could even take my rubber band and put it this way, and that's another great circle. So as long as it's going, as long as if you sliced it on that line, it would go through the middle of this sphere, it counts as a great circle. So again, I could even make it on a diagonal. Let's say I went like this, on a diagonal, right? That's still a great sphere, because if I sliced it in half right on that's a great circle. Because if I sliced this apple right on that line, it would go straight through the middle of the apple. So no matter how I line this up, okay, if it goes through, if the plane that I cut on this circle would go through the center of the apple, then this line is considered a great sphere. So there are really an infinite number of great spheres, okay? Now if I put the rubber band like this, and I just sliced off this little piece, that's not a great sphere, because that plane doesn't go through the middle of the apple. Neither does this one, right? It has to be fully around the fattest part of the apple, like that. Okay? Alright. One more page, turn it over. What happens when planes intersect with spheres? The intersection of a plane and a sphere is a circle. So let's just draw a quick picture of that again. We kind of talked about that already, but now let's just try to draw a picture of it, which is not easy. So let's say we took our knife and we cut that piece off of a sphere, right? What you would have is this small chunk. This is like this one here. You would have this small chunk, right? That would be that piece over there, which is a circle. It's a smaller circle though. And then you would have this other big fat piece, right? But it would still be the same size circle on the inside, and then it gets bigger as it goes to the outside. So essentially it would be another circle, and then the sphere would be like, you know, the other part that wasn't cut, you would still see the edge of a bigger circle on the outside, and then a little circle on the inside. Okay? Now here's an important fact. If two planes are equidistant from the center of a sphere, so let's draw our circle again. And we have a center. And we have, let's see, we have one, let's say we have one plane here that we cut, and let's say the distance from the center of that plane to the center of this sphere is r. And then let's say we took another chunk and the distance from here to this center was also r. Alright, so if they're the same distance away from the center of the sphere, then the two circles will be the same size. Okay? We would have two congruent circles. Now, here's a picture of that, right? If I took my apple and I measured the distance from the center and then I cut off a piece, and then I measured the same distance from the center, right? And I cut off another piece, then those two pieces, even though it didn't come out exact this time because I'm estimating, then those two pieces would be the same, those circles would be congruent if they're the same distance from the center of this apple. Okay? So, let's see. What's next? Oh, a hemisphere is half the sphere formed by a plane intersecting the center of a sphere. Okay? So a hemisphere essentially is that. Right? It's a half a sphere. Let's put exactly half a sphere. Okay? Now let's do the problems involving spheres. And there's a lot of them. Alright? So, hang on, let me sharpen my pencil. So, here's the first one. The radius of this sphere is 4 feet. Find the area of the great circle of this sphere to the nearest tenth. So you could imagine, you could imagine a great circle going right around the center, the biggest part. Now I could have drawn it this way, right? I could have drawn it this way. All that matters is that it goes around the fattest part of the sphere. And the center of the sphere is the center of that circle. Okay? So the radius of this thing is equal to the radius of the sphere, r, which is 4. Okay? So I'm going to take that circle out, and my radius is 4. Find the area of the great circle of this sphere to the nearest tenth. So area of a circle is just pi r squared. Area equals pi times 4 squared. Area is approximately pi 4 squared, 50 point to the nearest tenth, 50.3. 50.3 feet squared. At the age of 81, Mr. Luke Roberts decided to start collecting string. He has a spherical ball of string 3 feet in diameter. So if the diameter is 3 feet, the radius is half the diameter. The radius is 3 over 2. The radius is 1.5 feet. So 1.5, 1.5. In fact, let's just draw the radius so that we don't get confused. Okay? On the assumption that 1 cubic inch of string weighs 0.03 pounds, and the ball was solid string, how much does the ball weigh to the nearest tenth of a pound? So first we got to find the volume, which is, let me look up my formula, 4/3 pi r cubed. So the volume equals 4/3 times pi times 1.5 cubed. So the volume 4 times pi, times pi times 1.5 raised to the third power. We use that button. Let me move this up. We use this button, this caret button, to raise something to a higher power than 2. So that's 4 times pi times 1.5 cubed. I'm multiplying all my numerators together, right? And now I got to divide by the denominator, 3. So let's say it's approximately 14.1372. We go to 4 places, right? And that would be feet cubed. Okay. Now, it's 0.03 pound, 1 cubic inch. So 1 inch cubed equals 0.03 pounds. That's LBS is the unit for pounds. Okay? So if 1 inch cubed, is 0.03 pounds, and there are let's see, how do we want to do this? How do I want to go about this the easiest way? We want to convert either the volume into inches or this ratio into feet. Okay? Now, let's think. Alright, so I think the easiest way to do this would be to convert the feet cubed into inches cubed, right? Now think of 1 foot cubed. It would be 1 foot by 1 foot by 1 foot. Now if we, and that is 1 foot cubed. Now if we converted that, right, into inches, we would have 12 inches is 1 foot, right, and 12 inches and 12 inches. So 1 foot cubed is equal to, this is 1 times 1 times 1, that's how we got 1 foot cubed. So that's equal to 12 times 12 times 12 inches cubed. So 12 times 12 times 12 is 1,728 inches cubed. Alright? So now let's use this ratio to turn the volume into an inches cubed. So 1 foot cubed for every one is the same thing as 1,728 inches cubed. Then the volume is 14.1372 feet cubed. So how many inches cubed? You see how we set up this ratio? It's always got to be feet over inches equals feet over inches, or feet cubed over inches cubed equals feet cubed over inches cubed. It has to be the same things on the top, the same unit on the top, and the same unit on the bottom. Okay? So when I cross multiply, I get x equals 14.1372 times 1728. It's approximately 24429.0816 inches cubed. So we're not actually going to convert it this. We could have converted it this way also, but it's really the same thing. We could have converted the 1 inch cubed equals this many pounds to 1 foot cubed would equal how many pounds, all right? And we could do that a similar way. But I chose to do it this way. So now we have this volume, right? So this 14.1372 feet cubed is the same thing as this many inches cubed. So 1 inch cubed is 0.03 pounds. So then 24,429.0816 inches cubed is how many pounds? And we cross multiply. X equals the 24,000 number times 0.03. To the nearest tenth, X is approximately 732.9 lbs, pounds. Okay? Let's go to the next problem. When you blow up a balloon, it forms a sphere because it is trying to hold as much air as possible with as small a surface area as possible. How much air to the nearest tenth of a cubic inch is being held by a spherical balloon with a diameter of 12 inches? We have a spherical balloon. We don't care about the diameter, right? We want the radius. So if the diameter is 12 inches, the radius is diameter over 2. 12 over 2 is 6 inches. Volume equals 4/3 pi r cubed. Let me just, I always forget this one. Is it 4/3? Yep, 4/3 pi r cubed. So the volume is 4/3 pi times 6 cubed. Nearest tenth, so the volume is approximately 4/3 times pi times 6 raised to the third power. 904.8. And that's inches cubed. A cylinder and a sphere have the same radius and the same height. What is the ratio of the volume of the cylinder, so that one goes on top, to the volume of sphere? Okay? So let's do the volume of the cylinder. That's pi r squared h. Volume equals pi. We don't even have to plug in any values, right? Watch this. The volume of the cylinder is pi r squared h. The volume of the sphere is 4/3 pi r cubed. So the volume of the cylinder goes on top, pi r squared h, over the volume of the sphere goes on the bottom, which is 4 pi r cubed over 3. I'm putting this fraction together, right? I'm allowed to put all the things on top and the 3 on the bottom. Now I got to simplify this. So what I can do is multiply the bottom by 3 and the top by 3. That will give me 3 pi r squared h over, that 3 will cancel with that 3, 4 pi r cubed. Now I keep going. The pi's cancel. Okay. 2 of the r's cancel with 3 of the r's and leave me with 1 r left. So what I have is still I have the 3 and the h on top over 4 r to the first. So 4r. 3h over 4r is the ratio of the volume of the cylinder to the volume of the sphere. Okay? Next page. Sharpen my pencil. At the Metroplex movie theater, popcorn is served in a box. Right? At the Cinematplex movie theater, popcorn is served in a cylindrical container. Okay. And at home, Mom serves popcorn in a bowl, hemisphere in shape. Okay. So, okay. Based upon the given dimensions, where are you getting the most popcorn? It doesn't have the dimensions. Let me pull those up real quick. Okay, we have 10 inches, 5 inches, and 4 inches. And for the cylinder we have 8 inches, and the diameter is 6 inches. And for the hemisphere we have the diameter, which is 10 inches. Alright? So, based upon the given dimensions, where are you getting the most popcorn? Okay. So the volume of this is length times width times height, right? The volume is 4 times 5 times 10. The volume is 200 inches cubed. Now for the cylinder, it's pi r squared h. So the volume is pi. Now this diameter is 6. So my radius is 3. So it's pi times 3 squared times 8. So the volume is approximately 3 squared times 8 times pi, about 226. Let's just put 226, because I don't think we're going to need to go any further. Inches cubed. Now, the volume of a sphere is 4/3 pi r cubed. But since it's a hemisphere, we have to divide that by 2. Right? Divide by 2 because it is half a sphere. And we know that the radius is 5 inches. Right? So we're going to do volume equals 4/3 times pi times 5 cubed, and then divide everything by 2. Looks like complicated, but really it's not. You just have to plug it in right. Just do one thing at a time. 4/3 times pi times 5 raised to the third. Enter. Divided by 2, enter. 262. Approximately 262 inches cubed. Where are you getting the most popcorn? At home. Okay? A pharmacist is filling medicine capsules. The capsules are cylinders. with half spheres on each end. Okay? The length of the cylinder is 12 millimeters and the radius is 2 millimeters. How many cubic millimeters of medication can one capsule hold? Round answer to the nearest tenth. So what we have is a cylinder, so the volume equals pi r squared h plus, so wait, we have a volume of the cylinder plus the volume of a sphere, right? Because we have two halves, and the two halves of a spheres make a whole sphere. Two half spheres make a whole sphere. So what we have is pi r squared plus 4/3 pi r cubed. Okay? Volume equals pi times 2 squared times 12 plus 4/3 times pi times 2 cubed. So the volume is approximately, we're rounding to the nearest tenth, let's just do this slow. So what we have to do is this first part in parentheses and then the second part, because we're adding in the middle, okay? So we have to make sure we put the first part in parentheses and the second part in parentheses. So this is how we're going to do that. Parentheses, pi times 2 squared times 12, close my parentheses, plus parentheses. Now another parentheses for my 4/3, so 4/3 times pi times 2 raised to the third, close the parentheses, enter. 184.3 millimeters cubed. Okay? Let's see. Still got a bunch of problems left here, so hang on. Obviously, there's been a lot of Regents problems on spheres because these are all Regents problems. The sphere appears in nature whenever a surface wants to be as small as possible. Bubbles are an example of such a surface. If the diameter of a bubble is known to be 2, so we have a sphere, this time it's a bubble, right? And the diameter is 2 millimeters. So then the radius is 1 millimeter. What is the surface area to the nearest square millimeter? Ooh. Hang on a sec. Is this our first surface area problem? Just want to make sure I didn't mess anything up before. Yes, this is our first surface area of a sphere problem, which is a different formula. It's, let's see, 4 pi r squared. So this is not volume. This is surface area. Okay? So, surface area equals 4 times pi times 1 squared. Surface area is approximately, to the nearest square millimeter, 4 times pi times 1 squared is about 12 well, we have to round to the nearest millimeter, so it's 13. It's approximately 13 millimeters and area is squared. Okay, so here's a surface area problem. So it's going to be 4 pi r squared. It says the surface area is 144 pi, so 144 pi equals 4 pi r squared, divide by 4 pi, 4 pi pi, so we have r squared equals pi pi. Hopefully 144 divided by 4 works out to something even. It does. It's 36. And that's really nice because the square root of 36 is 6. Watch. 6. Okay? So it says, alright, we found the radius, but it wants the volume. So now we're going to use that radius to find the volume in terms of pi. So V equals 4/3 times pi times 6 cubed. So V equals 4 times 6 cubed is 864. Hopefully that divides by 3. It does. So we have 288 pi. And that would be units cubed. That's choice 4. Couple more left here. So volume of a sphere, 4/3 pi r cubed. Okay, sphere, the diameter is 6 centimeters, so that means the radius is 3 centimeters. So volume is 4/3 pi times 3 cubed. And they want it in terms of pi. You see the pi in the answer? So volume equals 4 times 3 raised to the 3rd divided by 3 is 36, so it's 36 pi units cubed. That's choice 2. The diameter of a sphere is 15 inches. They like to give this type of problem, huh? So then the radius is 7.5 inches. What's the volume to the nearest tenth of a cubic inch? 4/3 pi r cubed. 4/3 times pi times 7.5 cubed. So the volume is approximately, this time we're plugging pi in. So 4/3 times pi times 7.5 raised to the 3rd, 1767.1. And that's inches cubed. Okay? One more page. A sphere has a diameter of 18 meters. That means the radius is 9 meters. Find the volume in terms of pi. 4/3 pi r cubed. 4/3 times pi times 9 cubed. So we can do 4/3. This is another way to do it. Right? 4/3 times 9 cubed is 972 pi. And that would be meters cubed. Another one of these problems. Man, they love to give you these problems, huh? You better know how to do this one because these are all regions problems. Diameter is 12 inches, so the radius is 6 inches. The volume is 4/3 pi r cubed. Let me just, look at this. Surface area. This one was volume. Alright, good. So it's 4 pi r squared. So you got to be careful with that. Surface area equals 4 times pi times 6 squared, and they want it to the nearest square inch. So 4 times 6 squared, 144 pi. Whoops. I got to multiply that by pi because they want it as a decimal. 452.2 to the nearest square inch, so 452. Last one. A sphere is inscribed inside a cube with edges of 6 centimeters. So if you have a sphere, right, and this thing is inside a cube, right, and the edge of the cube is 6 centimeters, then that's the edge of the cube. Well, that's also the diameter of the sphere, right? So the diameter is 6 centimeters, so the radius is 3 centimeters. What is the volume and they want it in terms of pi. So we just do 4/3 times 3 cubed, 36 pi centimeters cubed. Okay, now this was a long one. Let's get this in order here. Our lesson was 2 pages, so 1 out of 2, 2 out of 2. And then we had 1, 2, 3 pages of problems. So 1 out of 3, 2 out of 3, 3 out of 3. Okay, and that is the end of the lesson on spheres and the end of the unit on prisms, pyramids, cylinders, cones, and spheres.